Let me welcome you to the 2025 Joel Lecture. A special occasion because the Joel Chair is believed to be the oldest chair in medical physics in the world, and so we therefore celebrate it by inviting a distinguished speaker. And today we certainly have a very distinguished speaker. But before I actually introduce David, I was going to run through a little bit to give you the background to the Joel Chair. Now, those that have ever been to a Joel lecture will know that this is fairly boring because I've given it so many times. But I'll try and put in the odd new piece of information if I may. Brilliant. Many thanks, David. I've got a little assistant to help me with the slides tonight. This is a diagram that is meant to demonstrate to you the connection between three separate entities. One of them is the Middlesex Hospital Medical School. One of them is University College Hospital Medical School, and the other one is the Joel Bonato family. So let me introduce you to those three streams. The top bar up here represents the Middlesex Medical School, which was established, as you can see, in 1745, and it was the first hospital, certainly the first hospital in London, that devoted a ward to the treatment of cancer, exclusively cancer. It had 6 beds and was run by a Mr. Whitbread, and he famously said, the little statement I put down there, that we either relieve by art or we are released by death. Those were the two options when you entered this ward for cancer treatment. In 1835, the Middlesex introduced a medical school, and the reason it introduced the medical school was because of the competition that was taking place, because University College Hospital also started a medical school, and if you look carefully, you'll notice that UCLH introduced a medical school 1 year before the Middlesex Medical School. And if you look at the minutes of the Medical School Council for the Middlesex, there's some really interesting comments about the fact that why on earth do we need a medical school? We're much better than University College just because they're competition, etc., etc. But the two medical schools were established. And then in this period, various important things took place, and with relevance to the establishment of the chair, it was very much the discovery of X-rays and ionizing radiation. But the bit that I wanted to draw your attention to were the two pictures in the middle here. These two people. They were two young men from the East End of London that used to earn money by boxing, doing conjuring tricks, entertaining people that were inside pubs and those sorts of places. They would go around the East End of London, entertain people and get given money for that evening's entertainment. And Harry, the one at the top, decided that he wanted to expand his entertaining and therefore went to South Africa, because at that time the diamond fields were beginning to expand dramatically, and therefore was a lot of money to be made and a lot of people to entertain. So they go over there, first Harry and then Barney, his brother, his younger brother, go over there, and they bought, having made a bit of money by entertaining people, they bought one of the mines that was believed to be no longer fruitful in producing diamonds. They paid the equivalent of 50p for this field, and they then managed to find some diamonds, so they made more money. Eventually, after 17 years, they sold out the company that they formed for £5.4 million to De Beers. And they went on to invest that money to make a fortune in gold mines, a fortune in horse racing, and to entertain themselves, they used to drive fast cars around Brooklands racetrack. They became a very rich family. There are a few disasters, and I'm limited on time because I know David wants to start talking, so I won't tell you about the disasters. But the family generally made a lot of money, and it's believed that some of the members of the family were treated for cancer at the Middlesex. So a large bequest was made to the Middlesex Hospital Medical School in this period here, that the 1912, they left a large sum of money with the strict instructions it should be used to enhance the treatment of cancer, or at least understanding of cancer. 3 chairs were decided to establish, one in surgery, one in chemistry, and one in physics. The physics one was appointed, as you can see, in 1920, the Joel Chair, and that was occupied by Sidney Russ, who was one of the first medical physics appointments in the medical school and the hospital. And that chair has then continued. And in 1988, to bring my story to a close, almost to a close, the University College Hospital and the Middlesex Medical School were merged when the University of London decided it didn't want 36 separate colleges, it wanted 6 major colleges. So many of the institutes were merged, and we merged, Middlesex merged with University College. And then University College has carried on, and unfortunately in a very small print, I don't know why it's got very small down here, David, but there's another important date that I wanted to indicate to you, and that is in 2015, there was the discovery of fast EIT. Now, I'm far from an expert in EIT, and David is the expert, so I will say very little more about that. So that's the reason that we are here, to celebrate this chair that was established in 1920, and it's arrived at UCL because of the merger between the colleges. Let me introduce David very briefly. I regard David as a really good colleague and a friend. The definition of a friend, I thought, was just a few days ago, he sent me an email and he said, I've got an important request. I've got a Cartier watch that needs repairing. And I looked at the request. I do a little bit of clocks and watches, but not very much in watches, and I had to say no. But I think the fact that he was prepared to trust me with a very expensive watch, I thought, well, that must be true friendship. I think I've said enough. I think I ought to introduce David and say, David, please give us the 2025 Joel Lecture.
Thank you very much. Good evening, everybody. Thank you for coming. This is really heartwarming to see so many old friends in the audience. And I can't believe that the grandfather of our entire field, Brian Brown, who's been my mentor, but also a real innovator, has come down all the way from Sheffield to join in. And he's founded the entire field of EIT. So I want to start by thanking Robert for this opportunity, because it's a really nice time to have a review of what I've been trying to do over the last 3 decades or so, since I've been at UCL and running the lab and trying to realize this vision of a new technique in neuroscience. And I'd also like to thank the medical physics department. It started with Dave Delpy, who welcomed me into the department in, I think, 2005, where UCL, our wonderful institution, wasn't quite sure what to do with a neurologist that had crazy ideas that involved engineering and physics. And this has been a spiritual home for me ever since then, which I've really appreciated. And I've had absolutely marvellous heads of department, Jem Hebden, Andy Nisbet, our dean kindly emailed me saying he couldn't be here, and then latterly Peter, who's a pal and now head of department as well, and also likes crazy ideas. So that's been marvellous. So I've had a somewhat unusual career, because basically I'm a doctor, but I like crazy ideas, and sometimes the crazy ideas take me into disciplines where I don't really know anything about it, but that never frightened me, and that's why I've ended up in the medical physics department. But the way I've done things, for better or for worse, is if I have an idea in something I don't know about, I go and find a stellar collaborator, of whom there are several actually in the audience, and they know what they're doing, and then in the end we manage to get things going. So I'd like to tell you about this idea of fast neural EIT, and also it's a very nice opportunity to review the achievements, but also the disappointments we've had over the 30 years. So this all started, I had the privilege of being an undergraduate in Cambridge, and we had wonderful lectures from Alan Hodgkin, who won the Nobel Prize for discovering the action potential, and also the late and great Colin Blakemore, who was a wonderful physiologist, and that converted me into wanting to have a career in neuroscience. And then there was in my final year, I did physiology and biophysics, And because in fact, people in my lab might not believe this, but physics was my best subject at school, even though I'd forgotten it by then. And then we had a lecture on spike coding in the nervous system from a physiologist called John Robson, and I thought this is what I want to spend my career doing. But then if you think about how to find out what the code is, there wasn't any way of measuring it. There wasn't one at the time, and I'd like to submit the argument that there still isn't one, even though we've made great advances. So I was a doctor for a bit, and then I basically wrecked my career by going off to Berkeley, because although I knew what I wanted to do was develop this new technique that could image circuits throughout the brain, which we couldn't do then and we still can't do now, and that would allow us to understand coding in the system, but at a human large circuit scale rather than individual neuron scale. So I knew I wanted to cross basically CT with EEG, but I didn't know how to do it. So in my 20s, I did have a reasonably promising medical career with good jobs, including National Hospital, Queen Square. And I basically wrecked it by, instead of going off to do an MD on how to lance boils on the bum, I went off and did a degree in biophysics in Berkeley. And I'd been told by everybody that it was impossible to come up with any new method. And when people tell me that, I usually don't believe them. And then I spent a year in Berkeley in the library going through all the changes in the brain, any technique that might be able to do this, and then came up with this crazy idea. And then UCL took pity on me, and I've been doing it here ever since. I'm now part of the woodwork. So a bit of background. Nobody would pay me full-time to do my crazy idea, so I've ended up being half a doctor, and then essentially I get my street cred from doing EEGs and EMG in the hospital, and that leaves me alone to do crazy things in the lab. So I'm clinical neurophysiologist at UCH, where I still see patients about half the time. And then we've got this wonderful research group in medical physics, and I run it with Kirill Ristovich, who's in the front there, who's an outstanding engineer. He's originally a mechanical engineer, but he's actually a wonderful mathematician and physiologist, and we now run the lab jointly. We've got a couple of postdocs, and I'll talk about Nicole in a moment, and then an interdisciplinary lab, which is half engineers, physicists, and half biologists. And so it's a bit like the Tower of Babel. They all arrive, and none of them can understand what the other lot are saying. And by the end of 3 years, we've got the biologists doing MATLAB coding, and then we've got one or two engineers that actually might do a hands-on experiment as well, involving live animals. And then also, apropos of fools rushing in where angels fear to tread, where we haven't got the capability, we've had some absolutely outstanding collaborators. At the moment, we're doing the first ever human vagus nerve studies, and that's with Andy McAvoy, who's a neurosurgeon at Queen Square, who's operating as we speak. He's probably been up since 6 this morning, so he couldn't make it. And then we've got Justin Perkins, who's transformed everything we can do, who's a large animal vet up at the Royal Vet College, which has enabled all the pig work I'm going to talk to you about. We've got cardiologists who are interested in our work on the vagus, and I'm very excited. Unfortunately, they couldn't make it tonight. We're now doing quantum physics, which I really don't know anything about and need the collaborators for. And then we've got a couple of other groups in the States where we go and do our vagus nerve stuff. And then we've also got some commercial collaborations. We had a really productive one with GSK and Google Health, who do this spin-out called Galvani Bioelectronics. We're collaborating with a commercial concern in Germany who I want to make EIT systems that we can then collaborate and start using. And then there's a new one with Merck. So what is this thing, electrical impedance tomography? This audience probably has heard of it, but just in case you haven't, I want to show you this fantastic video, if it's going to behave itself, which is from my mentor, Brian Brown, who's got the only paper on EIT in Nature. And what you do is you put rings of electrodes. This is the reason this is in Nature is normally EIT is you put 16 electrodes, ECG electrodes around the chest. You breathe in a small, completely safe current you can't feel is passed between different combinations of electrodes. That causes an impedance change, which you measure as voltages. You put them through a clever algorithm and you get a fuzzy picture of the lungs breathing. That's normally done with one ring of electrodes, but Brian, who's consistently innovated the entire field up at the Royal Hallamshire in Sheffield, did it with 4 rings of electrodes, and this is our only Nature paper in the field, and this is the sort of quality you can see of the lungs breathing. It's now been adopted by... Yeah, is it possible to turn that light off? Thank you, Sveta. Is that better? Yes. Thank you. So there's probably 40, and there's probably, since I wrote the talk, there's probably another 10 groups in China, so it's probably about 50. It was better with them all off, as long as you don't all go to sleep. That's fine, that's fine. Let's leave it with the lights down. Better just off completely, Sveta, I think would be nice. And then if I'm... Oh. Is that okay? Okay, sorry. So there's a lot of groups. There's now 6 companies, all thanks to Brian's lead on this. It can definitely image lung ventilation. It may be able to image cardiac output. And it can also image gastric emptying, and there's an example of it here. So this is an example in the chest. Here's one of the companies advertising for it. And I think in 10 or 20 years' time, every ITU bed will just have an EIT system, and you'll see the lungs breathing continuously at the end of the bed. It hasn't quite taken off in hospital use. And here's an example of 16 electrodes around the abdomen. The subject drinks some salty water. You can see an image like this. But that hasn't really found the use clinically. It was a bit of a Cinderella subject, but about 15 years ago now, some of the big medical device companies became interested in it, and then more recently, GSK became interested in it for our collaboration. So that's the rough background to it all. So my idea and work since I started off, I came back from Berkeley. I got a job as a registrar in neurology up at St James's University Hospital in Leeds. I was then, the young doctors nowadays had got it very easy, in my opinion, with their shift work. Then I was on a 1 in 2, and on my nights off, Brian took pity on me and gave me an impedance measuring circuit. And so on my nights off, I'd go over to the biophysics department and make the first EIT measurements. And then at the end of that time, he lent me an EIT system. It's the most famous and best EIT system, which is called the Sheffield Mark I. And this is all the work we've done since then. So what is EIT? Technically, this represents a current source. Let's say you have 16 electrodes around a tank of salty water. You'll apply the current to a couple of electrodes, then you'll move it round, move it round, move it round until you've addressed all the possible electrode pairs. You make lots of voltage measurements, and those are illustrated here. And then from that, because you've got the voltage and the current, you can measure the impedance. You put it through a finite element mesh, which for the non-engineers is like a triangular mesh, computer model mesh, and do some very clever mathematics, and you end up with an image. And we've been able to show that with that, you can image activity in the brain, providing you put electrodes over the brain. And the basic principle of this all is that this is a blown up section of a nerve or a neuronal process in the brain. It's got tiny little channels in it, and activity occurs as these channels open, the impedance falls, and therefore we're measuring the impedance. The trouble is, it's not a very big signal, and it's on the end of signal noise. So over the last, we've been working on this for 30 years. We definitely got it to work 10 years ago. And this is the the great dream of fast neural activity. We've also worked on a related technique, which I call slow activity, and that's because this signal is a bit small, but it also turns out there are impedance changes when you have functional activity in the brain and more blood flows to that part of the brain. That's much larger and easier to measure. That's a bit like functional MRI. And so we've done work on that I want to talk about in a moment. We've also had an idea of using this for stroke and head injury in the back of an ambulance, but I won't be talking about that tonight because there isn't time. So the vision that I had as the medical student all that time ago was this, that if you're an electrical or electronic engineer, you have an unknown circuit, you can get an oscilloscope, you can measure various places around it with your oscilloscope, and then you can work out the circuit diagram. We can't do that in the brain. The brain probably has got a few score of major circuits, they're very good models now of how they work. They're probably all control loops and nested control loops. So the idea was that we would have something that looks like an old-fashioned beehive hairdryer, put someone in it, do some cognitive task, such as showing them a picture of their grandmother, and then you would get an image that looks like this. These are different slices through the brain that look similar to functional MRI or CT, but we would get one of these every millisecond. You could put your virtual probe in, get the waveform, and then you could use that to refine the different models that people have of brain function. That's the great vision. Now, at this point, I understand nowadays you've got to disclose any conflicts of interest. Well, this isn't really a conflict of interest, but the story is that in the past, we used to get most of the grants I applied for, because people, I think, saw what we were doing as being pretty novel. Since lockdown, it's got a lot more difficult. I'm not quite sure why. We might be seen as old hat, it might be seen as too difficult, but we've had a few grants where we've got 9 out of 10 scores and still didn't get the funding. So I made a decision, for better or for worse, that we need to start a spin-out. But the spin-out isn't for me to have my own yacht and private jet. The spin-out is in order to support the research in the group. So I have to come clean on that. And I've been supporting it personally. I had a couple of meetings with our VC people, and that wasn't very encouraging. So I'm supporting it myself from my private practice, and it's been marvelous. It's given us, in part, support for 2 or 3 students in the group. It's a catalyst for small projects and pilot projects. And also, we've had 2 patents granted. I'm pleased to have been helped by a most marvellous patent attorney to do that. And I have to tell you the story. I think we're okay for time. I'm a humble clinical neurophysiologist and clinical academic, so I don't often get a Christmas hamper, but I got my first and probably last Christmas hamper from Bolt, Wade and Tennant last year, because I'd been such a good customer in the previous year, so that was much appreciated. So we protected this, and I'm hoping at some point this will bring in some income that will allow us to continue this crazy research. So the main ideas, I don't want to go and spend too long on this, the main idea is, so most of the interest around the world is in chest EIT, but it's done with a single ring. But companies will normally sell this at commercial medical device rates. So they'll sell an EIT system for 20 or 30,000 pounds, and then there's some electronics on the belts. They'll charge a few £100s for each patient. I had the idea, and I've always said that EIT is the McDonald's of the medical imaging world, that we need to make it cheap and cheerful. So idea number 1 is we'll make these belts, instead of ECG electrodes, all of silicone rubber. They're conductive silicone rubber and just ordinary insulating silicone rubber. They've got to be of a design that anyone, anywhere in the world can buy off Amazon, put on, and it just works, so they're self-abrading. And I think you can make those, once we get into work, for £2 or £3 if they're manufactured in bulk. As part of our GSK collaboration, we had a marvellous collaboration with Samsung, and they put the whole electronics of EIT on a single chip. And if you can put the whole lot on a chip, you can make those for £1 or £2 each. So my idea is we make all this for £1 or £2. We follow Brian's Nature paper by making it 4 rings rather than 1, so we get true 3D imaging of the chest. And then when there's the next COVID, or we need to monitor lung function in telemedicine, these will be selling in millions. That's at the prototype stage. I patented it, and it was granted. And when the prototype is working, we'll be going out to investors. The other one is we've developed, largely thanks to Kirill, the most sensitive EIT system in the world that can measure these tiny changes in the brain. But it's a bit Heath Robinson, and we're collaborating with groups, but the only way we can get it to work is if Kirill and the lab fly out and we do it, because it takes a year of the brightest postdoc to learn how to do it. So I want something that won't fall to bits in the post, and we can start getting neuroscience groups. And so this is our collaborating company. It's still got a few hitches, but we're hoping that we can either get this or something. And when that's ready, we want to go out and start selling it to collaborators. Finally, we've had a very successful nerve project I'll tell you about in a moment with GSK, and they've taken out 7 patents with UCL, and 2 of them have been assigned to my spin-out, and then we hope we can license that. And then finally, the pot of gold at the end of the rainbow is going to be able to do this fast neural EIT with a very novel design that involves quantum physics using these atomic magnetometers. That is still in development. We don't know whether it's going to work, but that's been patented as well. So those are the 4 ideas. But I don't think it's a conflict of interest, because if any of them make any money, it's going to be ploughed back into the group. So having had this great idea a very long time ago, there was always the possibility that we didn't need it anymore, even if we got it to work. So I'm sure you are all well aware that it is now very topical to do neural EIT. Elon Musk company Neuralink is very popular, and there are lots of other companies in that space. So in a couple of minutes, what else is there? And does this mean that my great idea, even if we got it to work, wouldn't be needed? So the first is, what can you do with electrophysiology? You could have done that 30 years ago with depth electrodes in the human brain, but you only had a handful of them. With the CMOS technology, you've now got really impressive advances where you can have multi-electrode arrays, such as the NeuroPixels is probably the best known, which there are people working on this at UCL. They have literally thousands of connectors. And the main thing when you've got thousands of little connectors you put in the brain is you can make the measurements, but your switches are too big. So using CMOS silicon technology, you can get the switches, and you can record from thousands of neurons at the same time. The problem with that is that's great, and you can look at local neuronal models, but you've got 10,000 million neurons in the brain, and it's undersampling. And when you measure potentials like this, and this is the main competitive technique to what we're doing with fast neural EIT, there is no true image that you can form from potentials alone, because there are lots of possible explanations that would explain any potential map. You can make approximations, but you can never be sure how accurate they are. The next thing that's really burgeoned over this time is being able to image functional activity in the brain with functional MRI and also positron emission tomography. Now, these measure slow changes over seconds related to activity, and but they've been very widely used in cognitive neuroscience. I think you might argue that they haven't produced any truly paradigm-shifting discoveries, because before fMRI, you could make a pretty good hazard as to what the function of different parts of the brain was by seeing neurological patients who'd had lesions in different parts of the brain. But they've certainly helped refine models, for example, the dual stream model of language processing we're showing here with fMRI studies, but it won't allow you to understand how the brain processes information, because changes over seconds represents the integral of many thousands of activities. So it tells you where it is, but not how it's working. Then there's this other exciting development based on laser technology, where you can get an animal, you can genetically encode the neurons in the brain, or you have a dye that produces a light signal when calcium influxes during activity. This is 2-photon calcium imaging. It's extraordinary. You can focus on up to about 1 cubic millimeter of the brain, rather like neuropixels, you can image up to several thousand neurons, and that has been truly unique in allowing us to look at local models, but it's only 1 cubic millimeter. It hasn't been used in humans, and it's calcium, which occurs over hundreds of milliseconds, rather than the sodium flux, which occurs over milliseconds, which is the way the neurons really work. This certainly helps a lot at local level. And then finally, and I'm sure everyone is aware, there's been a huge expansion of artificial neural network modeling of brain function and these many circuits. And this is a very exciting area. And this area can draw on the above techniques in order to try and validate their models. But in spite of that, now there's some tentative methods, I think, and I don't know if there may well be people in the audience who know much more about this than I do, I still don't think that there's any method we've got that can image at the level of a human brain, see all these major pathways, the envelope activity, and do it over milliseconds. So this is the outline of my talk, and with my artistic side is I like the traffic light analogy. So when I put things in green, it means that's good and it works. Amber means it might work, and red means it didn't work. So anyway, so that's my clever color coding on the outline. So I've given you the original vision. I'm now going to give you a brief introduction to how we do this fast neural EIT, and then we'll come on to the things that worked and the things that sort of work. So bear with me on this slightly busy slide, but I thought for the physicists and engineers in the audience, this would give you an idea of how the technology is, and I'm illustrating it with respect to our imaging in nerves. So I don't know how clear that is, but this is a graphic of an anesthetized pig. The pig has got lungs and a heart, and it's also got a larynx. And the vagus nerve, which is the nerve of interest, supplies all of them. So we take the pig, we wire it up with an EIT machine. This is our current EIT machine. And it's conceptually quite simple. Originally, we used to make all the electronics ourselves, as did Brian Brown with the Sheffield Mark I. In order to get the maximum sensitivity, we in fact use a commercial, very sensitive current source. We have a very well-specified EEG amplifier to measure the voltages, and we have our own switch box and ways of controlling it, and that produces images like this. So we hook that up to a cuff, and we've made our own cuffs which have got this geometry. They have 14 little electrodes around the vagus nerve, which is about 3 millimeters across, and here's a graphic of that. We can do the EIT imaging with one ring of them, and then if we want to then stimulate the nerve and stimulate different parts of the nerve, we have 2 rings, and you'll stimulate through 2 of the electrodes, and that will locally activate it. So the way the technology works is to generate an image takes a few minutes. Now, why does it take a few minutes? Well, in order to do tomography, for example, you take the analogy of X-ray CT. With X-ray CT, you beam an X-ray through part of the body you're interested in, take a measurement, and then you do that very quickly, and you can spin round very quickly. We do the same conceptually in EIT, but in EIT, we apply a current, a small current. So we'll start off by applying a current with our current source, say, to 2 electrodes, normally spaced a few electrodes apart. And that'll usually be at a few kilohertz, about 6 kilohertz. And then we'll continue doing that for 30 seconds or a minute. So why does it need to be that long? Because, of course, an action potential in the nerve just lasts a few milliseconds. And the reason is the signal is small and noisy. So what we do is we do the technique of averaging, in which you repeat something, you keep adding it to itself, the noise cancels out, and you're left with the signal. And we average to the ECG, or maybe breathing, or else we might put some electrodes in and trigger the larynx. So that will be, say, 30 seconds. We then switch to another pair of electrodes, another 30 seconds, another 30 seconds, and so to get an image in the nerve, by the time you've finished, is a few minutes of averaging. You apply a constant current at a few kilohertz, and the impedance change in the nerve modulates that. So this is shown graphically here, and that means it's a bit like AM radio, which you've got a carrier and it's changed by the voice in AM radio. In our case, the nerve activity modulates that. You end up with a signal like that, you average them all together, and then you get a data set like this, where along here, this will be time of, I don't know, 100 milliseconds or so. This will be impedance along here, and you'll have about 1,000 different of these transfer impedance measurements. Then our mathematical collaborators do something very clever. We use this finite element model, put it through that, and then you end up with an image of this, and this is an example of the cross-section of the nerve. You've averaged over several minutes, but by the time you put it all together, you're seeing something that's just, if you see down here, it's just lasting a few milliseconds. Sorry. There is no other technique in the world that can do this. It's only EIT, and we can see. So that's the technique. Now, I showed this, I ran it past our lab group yesterday, and Kirill told me that there's too much technology in it, and if I really want to keep that talk, it was 3 hours rather than the 40 minutes I'm hoping for. So this is the one slide he's allowed me to keep in, because I think this is interesting, and then I'm not going to talk about technical details, because I want to give you the bird's eye view. But this is a technical, because you might say, well, if you're trying to image something that's a few milliseconds long, why do you have to wait 10 minutes to get an image? This is driving our potential users away, and the trouble is you can't escape it. So I'm sorry if it makes your brain hurt, this one. It certainly makes my brain hurt. So what's the principle of the impedance change, which I can thank Alan Hodgkin, who I had lectures from, who discovered the action potential. If you can imagine a nerve like this, the nerve has got these ion channels in it. We are applying a current across that nerve, and the membrane of the nerve is a lipid, so it's a resistor. So if you apply a DC current at rest, it won't go into the nerve because DC current can't cross a resistor lipid. And then when the ion channels open, when the nerve fires, that current can go through the nerve as well, and there's salty water in the centers. That means there's an impedance change. Sadly, it's not very big, it's only about 1%. And so all our original measurements were made at DC, and we had to average forever, not minutes, but hours or days. And the reason is, if you try to do it in the brain annoyingly produces voltages at about DC, which are miles bigger than what we're trying to measure, so we couldn't measure anything. And it's the same in nerves. They annoyingly produce voltages at about this. So then we had the inspiration that maybe we could apply alternating current, which would take us away from the annoying EEG. But it's the devil in the deep blue sea, because if you apply an alternating current, this very thin membrane in the nerve acts like a capacitor, and capacitors allow the alternating current through. So it starts to go through at rest, and therefore the difference when those ion channels open isn't as big as at DC. So that's much smaller. So we've done a lot of experiments in order to find out where the sweet spot is, and that's how we finally got it to work. So these are two critical graphs, and then I'm not going to be technical anymore. So this is in nerve, and these are kilohertz. We're going up here to about 100 kilohertz. And the sweet spot here, which is about 6 kilohertz, means that that's where we have the highest chance of measuring anything, and it's already pretty annoyingly small. In fact, it's right on the edge of what you can measure. The blue thing is that the signal processing theory says if you want to measure a change of a few milliseconds, just as you do in AM radio, you have to have a bandwidth around this critical frequency of whatever of the time constant of the signal. So we measure it about 6 kilohertz plus and minus 1 kilohertz or half a kilohertz, so that represents here. In the brain, it's rather lower, and it's about 1.5 kilohertz, and then we also need that. In the brain, it falls off very rapidly. So the implication is we can only make these measurements at one frequency in both cases, which is why we can then have to switch through all 30 pairs, why it all takes 10 minutes. And it's a small diversion. One of the pleasures of being very elderly like I am now is that you can look at the people in your group and see how they've come on. And I'm very proud to say that I think we've got, the last count, 4 full chairs of people who've been my students and postdocs, 2 of whom are in the audience. And we've got 3 new lecturers as well. And one of them sitting over there is the student who produced this marvellous graph of the maximum sensitivity, which is Sana, who's just recently got a lecturer position in Lancaster. Right, so now I think we're still on time. So what has worked of all this thought and activity? So when I started, we used to use nerves in order to validate the principle of what we're doing, but I never thought that that's what our main success story was going to be. But about 10 years ago, we had a marvellous meeting here at UCL where someone at GSK had come up with the idea that they wanted to improve vagal nerve stimulation. So this is now a fairly mature medical treatment. The idea is you stimulate the vagus nerve, it's widely used in epilepsy, and it works even though people don't really understand why, with about a few 100,000 implants. And GSK are interested because it could be used for other things, because the vagus nerve can also affect endocrine and immune function. And it's quite possible in 10 years' time there'll be millions of patients with these conditions walking around with little chips in their neck. But the thing that bedevils it is the technology until now means that they put one wire around the vagus nerve, and the vagus nerve supplies about 10 different organs in your chest and your abdomen. So you're stimulating organs you don't want. So the efficacy has been limited by this off-target stimulation. So our solution, which has largely been pioneered by Kirill, is to design this new nerve cuff. It has 14 electrodes in rings like this, and the idea is we use that to image what's going on in the nerve, find the bits that we want, and then you can stimulate the ones that you want. But when we started, unbelievably, there was a physiological challenge to this. So this is a nice diagram of a nerve. If you look at any nerve in the body, and you do a cross-section of it like this, you can see there are mini nerves inside it. They're called fascicles, where the nerves are bundled. And these fascicles are well known. And in the limbs, and I'm very pleased to say we have old pal neurophysiological colleagues in the audience who know all about this, it's pretty well understood that each of these fascicles logically supplies a few muscles or a bit of skin. But nobody knew what they were linked to in the autonomic nervous system, because nobody ever studied it. So we had very nice funding from GSK, but it could have been that if one organ didn't map to one of these fascicles, we'd have been wasting our and everybody else's time. So it wasn't known. We got about 10 in the human and the vagus nerve. So the question is, could we find out? There were 2 questions. One is, what was the linking of these fascicles to organs? And then secondly, could we selectively stimulate them? And just as another aside, I think it's very important, if you are presenting a new technique, you don't just present your technique and say how wonderful it is, you honestly compare it to the competition. And the competition in this space is that there's this idea that you could put a cuff around a nerve, measure the compound action potential, that many people are doing this, and then you could take those voltages and do this inverse source modeling thing I've already referred to. Well, we did a proof of concept study, and these are the EIT images. So this is in a rat sciatic nerve. The rat sciatic nerve has got 3 main fascicles called tibial and peroneal and sural. And when we, with the EIT, you can see we've got nice clear images. And when we tried to do this inverse source modeling, in theory, it's not going to be as good, and in practice, it was hopeless. So I like to think we're not just doing this because we can do it. It is actually better than any other available technique. So the bottom line of loads of work, and again, I'm pleased to say we've got members of the team who are in the audience, is that we found for the first time that their fascicles in the nerve map to the heart, to the larynx, and to breathing. And this had never been known before. And here's a graphic of it like this. So cardiac, pulmonary, and this was all statistically significant. Just to remind you of the way we did this, we'd take an anaesthetized pig, we'd measure its breathing, you would average for a few minutes off the breathing, and then which one's the pulmonary? That's the pulmonary one. Then you would find that this is your cross-section of the nerve. The fascicle there was the breathing-related one. You measured the ECG and you found the cardiac one, which is that one, and they were separate. So this meant, for the first time, that if you wanted, say, to treat heart failure, you could put one of our cuffs round. In that patient, you could find out which the cardiac fascicle was, and then you would use the 2 electrodes to selectively do that, and you wouldn't be affecting respiration or the larynx, making them go hoarse. So this is quite an important discovery. So having come up with this, there's many a slip twixt cup and lip, and we need to show that it wasn't all artifact. So we decided that we needed to independently validate this, and this has been a major triumph, and it's largely due to Nicole, who's now a postdoc in our group, and she pioneered a new technique as a PhD student. So the technique is, how do you definitely know that this is true? Well, you can take a pig, and this is Nicole asleep on the floor of Justin's lab at 3 o'clock in the morning. These pig experiments were heroic. Justin, being a surgeon, doesn't need to sleep, and so they'd start at 9 in the morning and finish at 4 o'clock the next morning to get all our data. And then at the end of this, Sveta, who's also here, and taught Nicole how to do this, would wade into this enormous animal and dissect out its vagus nerve all the way from the neck all the way down to its to the end organ, take that out, put it in a micro CT scanner, and this had never been done before. People had tried to do it, but they only ever managed a few centimeters. Nicole, even though she's only a biologist, did all the physics and worked out how to do this for length of nerve this long. It'd never been done before. It's now been adopted internationally. You would then do heroic tracing to come up with images like this. And here is a lovely video of going down the whole length of the nerve. And we were able to show that these were linked to the heart and lungs, and it matched what we found on the EIT. So this is quite an important discovery. Then we also independently validated it by taking the cuffs like this. You could stimulate at different places, and you could show that they affected heart and lungs. I haven't got time to go into that, and that has been Kirill's work. And just to follow on from this, we're now doing, this is all done in anaesthetized pigs, but we're now doing a human study. I'm afraid our neurosurgical colleagues are still working, so not here. We've got another of the new lecturers in the audience who's helped us develop this cuff, which is now suitable for human use with the UCL dimensions, Chris Chapman, and with it we can localize the cardiac. These are still preliminary studies, it's in progress. We found the heart-related fascicles, and we're in parallel doing a human study on human cadavers in which Nicole and our new team are tracing these in order to show what the human mapping is, excuse me, compared to the pig. And we've got very nice MRC funding for that. So now that works, I think, and the reason it works is it still takes minutes to collect one of these nerve images, but it doesn't matter, because if you've got an experimental animal, or eventually where you're in a human and you've got an implanted chip, it doesn't matter if it takes a few minutes of triggering from your ECG to find out what is localized. So I like to think it fulfills the original objective. Now the next one is using slow EIT in epileptic seizures to see where the seizure is starting from. So the clinical need for this is I and the other clinical neurophysiologists in the audience see patients with epilepsy all the time. Normally you can diagnose it with an EEG. Some of them have got severe resistant epilepsy, they need surgery, and if you're going to remove part of the brain, you really need to know where that part is. And so they'll come in and they'll have electrodes put in the brain. Now, the principle of the impedance is different to the fast neural. So if you apply a current now up to about 100 kilohertz, and these are now supposed to be brain cells, normally it will go through the extracellular space and not much will go into the cells. During an epileptic seizure, the cells run out of energy, they can't control their volume, they expand, and the extracellular space shrinks. The current still isn't going into the cells, and so you get a nice big impedance change of 10 or 20% over a few seconds. So it's much easier to do, and you can therefore turn EIT into a parallel system, which means you can do this in real time. You don't need to do all this annoying averaging. The problem is, this is not a unique paradigm shifting method, because like fast neural would be, it's very similar to having someone in an fMRI scanner when they have a seizure. It's not very practical because you can't put someone in an fMRI scanner for a week. So it could have practical advantages, but I don't think it's paradigm shifting. So we've got two people in the audience who did the pioneering work on this. Lorenzo and Tom Tidswell. Lorenzo is now one of the 4 chairs in our group, and Tom is now a leading clinical neurophysiologist. This is Lorenzo, you probably can't see him there, and he did this pioneering work down in studies at King's. Tom was responsible, I think, for our most cited ever paper, in which he did these slow changes during activity. This photo is my favorite photo in the 30 years I've been running the lab. I don't know if you can see, it's not very big, but it's his son Zach with a couple of big goggles on so that he could do visual evoked responses. And I'm so old now that Zach is now a 6'4" strapping athlete and dancer. That is my favorite photo of the entire 30 years. And so that's the basic idea behind it. Very quickly, does it work? Yes, it absolutely does work, and this is an example of it. We did with Justin as collaborator, Kirill and our other team went down, took human electrodes, intracranial electrodes that had been used in humans, washed them, put them in the pig, a anaesthetized pig, and you could see the epileptic seizure starting and spreading. So, and it correlates to where the seizure was starting. This, therefore, is a method that I think could be tacked on to this intracranial EEG that is done in units all around the world in these epilepsy patients. And the next step is to do human studies. And I think that in 5 or 10 years, this will just be piggybacked on to every intracranial EEG. Now, what sort of work? This is the partial disappointment, because I hope that now, after all this time, we would be able to put the beehive hairdryer on, show someone a picture of their grandmother, see all the circuits lighting up, and all our computational neuroscience colleagues, as in the world-leading Sainsbury Wellcome Centre at UCL, will be beating a path to our door. And it sort of works. So does it work? Yes, it does. But, so here's, let me just show the technique. We make our own electrodes. I don't know how clearly you can see that, but essentially this is platinum foil. We laser cut into lots of tiny electrodes, about 0.5 millimeter across. We put 120 of them on the brain of a rat. So in order to do that, it doesn't work if you do it on the scalp, because the skull makes the signal too small. So limitation number 1 is it's got to be intracranial, and that kind of limits your choice when you want human volunteers to be the subjects, sadly. And the second thing is, it works, but you've got to average for 10 or 15 minutes. Now, if you're a cognitive neuroscientist and you want to show someone a picture of their grandmother, if you have to do that 300 times, they're going to get a bit bored. And so those are the limitations, but it does work, and this is all published. There is no other technique in the world, as far as I know, because look here, these are changes over milliseconds. We can see activity anywhere in the cerebral cortex of the rat, changing over milliseconds and with a resolution of 1/5 of a millimeter. So with it, again, at the expense, intracranial electrodes and averaging over minutes, we can watch the propagation of epileptic activity through the cerebral cortex, through the different cerebral layers, and that again is Sana's work. And then this first studies were all through the depth of the cortex, and which is a few millimeters. And Sana also showed that again, this is the experimental paradigm, just to illustrate it. This is a rat brain with the electrodes on it, that if you choose the hippocampus in the rat, which is about a quarter of the way through, we can image epileptic seizures occurring a quarter of the way into the brain using these electrodes. So that works as well. So to summarize, another 5 minutes. Roberts did have a rather long introduction. Are you okay? Can you bear with me for another 5 minutes maximum? The vagus nerve project, I think, works and it fulfills the original objectives. And it definitely works. We could use it for research groups straight away. I'm not sure whether the dream of Galvani and now other companies is right, and that in 10 or 20 years' time there are going to be millions of people with selective vagal nerve stimulators walking around. If they are, I think it's perfectly possible that they will have EIT chips in and be doing EIG imaging. Slow brain EIT works in animals. We now need and want to do it in human subjects, so we need collaborators for that and to be able to negotiate the politics of that. For fast neural EIT, we've shown proof of concept, but the next step is, number one, to get collaborators using it, because it may be there are neuroscience groups that would still find it useful. But what we really want to do is go to the original vision of something where you don't need to drill holes in people's heads and it works in real time, and we think we have a way of doing that. So this is the idea that EIT, as it was invented by Brian Brown, uses, you inject an electrical current and you measure the electrical voltages. It's a very good idea in the chest. So the annoying thing in the brain is you've got the skull, and the skull doesn't like having electricity injected through it. So there's a new technology, independently produced, not because of us, where you can measure the tiny magnetic fields in the brain. And it's called an atomic magnetometer. They're room temperature, they're this big, and you buy them for a few £1,000s. And then there's also something you may have heard of called magnetoencephalography, which is done with super-cooled quantum technology called squids. This is a very expensive one. We have one at UCL over at Queen Square. And the idea is you still got to use electrodes on the scalp to inject the current at our sweet spot frequency, but we'll measure the resulting signal with these magnetometers. Because magnetic fields go straight through the skull, that should give us much better images. And we've done proof of concept studies with modeling and tank studies, and it looks like it should give us an advantage. But there are a couple of big challenges. Firstly, you need to be able to do it in humans, and secondly, the magnetometers, which are very tricky to make, they require advanced quantum physics and design skills, are all optimized for human studies at very low frequencies. They don't like being used at our higher frequencies. So we're collaborating, got marvelous collaborations, unfortunately they couldn't make it, with the equivalent of the National Physical Lab in Berlin, and Peter Kruger, and also Stuart Ingleby, who's up in Strathclyde, who, unlike me, apparently understand quantum physics. And this is the next step, to get these magnetometers and see if we can get that to work. But we proved principle in tank studies. Finally, can we do it in real time? So the reason this annoying requirement for taking tens of minutes is because from these graphs, which I won't bore you with again, there's only one sweet spot. Maybe, so this is frequency along here. Most EIT in the chest is done much up here at much higher frequencies because it's fine, you still get the physiological changes. We, to start with, always said, oh look, the signal is too small in this band up here, say 20, 30 kilohertz. But we're collaborating with an outstanding group at Columbia University in the States who can make very low noise CMOS EIT systems, and also at the same time penetrating shanks for the brain. And we think we may be able to get enough signal to noise up at the much higher frequencies. And if you can do that, then this is imaginary, this is just to sketch it. This is your signal to noise, this is the frequency in kilohertz. Maybe we'll get enough signal up at, say, 40, 50, 60 kilohertz. We can do it in parallel, and that's going to be real time. So maybe these two things will work, we can't be sure, but it's very exciting. So to finish, where are we? We would like to be able to EIT image in epilepsy and cognitive neuroscience. And then that's not our work, but there's marvelous things going on in the world of neural engineering. Once you know what part of the brain you want to modulate, then you can do it, and there are ultrasound and other techniques for doing that. And then in nerve, similar idea. And what we want to do in both of these is human studies. So to finish, in summary, let's set that one off. Does fast neural EIT work? Yes, definitely works in the brain, but with these limitations. And it definitely works in nerve, the fascicles, I think without limitations. So we've got plans over the next 5 to 10 years for our group, which I think will be led by Kirill, as I'm long in the tooth now. The two, I think, realistic ones are we want to start making our techniques available to neuroscience researchers and ideally clinicians as well, and in also animal neuroscience and human epilepsy groups. It may be that EIT comes to be used in millions of these vagal nerve stimulator implants, and maybe if we can crack this nut, we can achieve the original goal of being able to image the brain in real time. And I'd just finally like to end by saying that I am very grateful to all of you. It's lovely to see all these friendly faces in the audience. I invited a few other people. I invited one of my colleagues in academic clinical neurophysiology in Newcastle, who wrote to me saying that sadly he couldn't come, but congratulations on your retirement. And I said, unless you know something I don't think, and sort of Peter, my new head of department, knows, I don't think I'm retiring yet. And so all I can say is I'm definitely long in the tooth. I never thought UCL would tolerate me for this long. I'm part of the woodwork. But I'm just as enthusiastic and excited by this as I was when I set out to do it 40 years ago. And at some point I'm going to have to hang up my hat. But we've got a marvellous group, which is led by Kirill, and a good, strong group. And I think we do actually have we can do this thing, and I don't want to give up until we see whether we can implement these two new ideas and achieve the original vision of something that I think would be a significant new technique for neuroscience research. Thank you for your attention.
Well, David, thank you for a very, very interesting talk. Actually, far from retiring, I was actually going to ask Robert, can someone give a Joel lecture twice? Because in 10 years' time, we need to see the update. So I was thinking about, is there a word that I think about when I think of David? You know what? The word challenge kept coming to mind. And the challenge is because you like to challenge physics, you like to challenge engineering, and you like challenging problems. I do sometimes have to mediate between Kirill and David, not in a relational sense, but because sometimes David wants to do something that's not possible, and I have to help Kirill to explain that that's not possible. But then sometimes these ideas actually do lead to a way around to do something in a way that we didn't think was possible, but but ultimately may be possible. So, Robert has given me this medal to give to you, which is the Joel Lecture 2025 medal. So, congratulations, David. Thank you for an excellent talk.
Thank you, Peter.
And we look forward to seeing the realisation of this goal in due course.
Thank you, Peter.